Hello, I'm Duncan Lockerby from the University of Warwick, and I'm going to talk about multi-scale simulation of Knudsen pumps. But I'll start by just acknowledging my co-workers and also the EPSRC who fund this work in the UK. And I'd also like to thank this group from the University of Marseille who provided me with some of their published experimental data, and also Nicholas Hadjiconstantino from MIT, who provided us with a LVDSMC code, which I'll explain a bit more later about. Okay, so the main purpose of this talk is to introduce you to multi-scale modelling methods that we've developed over the past few years, and I'm going to use the Knudsen pump application as a means to showcase those methods. So I'll start by explaining what a Knudsen pump actually is. A Knudsen pump is a gas pump that has no moving parts, and the pumping is generated by temperature difference. So here you see two reservoirs connected by a channel, and one of those reservoirs is heated and one of those is cooled, creating a temperature gradient. And so there's no pressure difference applied here, but that temperature gradient, if the channel is small enough, so if it's comparable to the molecular mean free path, that temperature difference will actually drive a flow from the cold reservoir to the hot reservoir. And that's a rarefied gas effect that was observed in the late 19th century by Reynolds. So that's called thermal transpiration, or sometimes it's known as thermal creep. So the Knudsen pump works because that flow from the cold reservoir to the hot reservoir creates a pressure change in the hot reservoir as more mass gets transferred. And that pressure difference then drives a flow back from the hot reservoir into the cold reservoir. So what you have is a zero net flow in the steady state. So there's a core region of flow going from the hot to the cold, and near the walls of the channel there is a thermal transpiration flow from the cold to the hot. Now the guys from Marseille I mentioned earlier, they investigated experimentally the transients of that phenomenon, and so what they did, they connected those two reservoirs such that the pressures initially were equal. So they set up the heating beforehand. That creates a thermal transpiration flow, and then at some point in time they close the valve that connects the two reservoirs, and the pressures then diverge and then go to a steady state, and the pressure in the hot reservoir is higher than that in the cold reservoir. And the reason those pressures aren't symmetrical is because of the two volumes aren't actually the same in their experiments. So that's the actual experimental data. Now, what we would like to be able to do is simulate that sort of flow problem. And why is that a challenge? Why is that not a trivial task? Well, first of all, the channel width, the channel radius, that is too small for conventional CFD to be accurate. Thermal transpiration is a non-equilibrium rarefied gas effect, and that's not something that Navier-Stokes and no-slip boundary conditions can capture. So that channel is too small. But on the other hand, a full particle or a molecular method which would be accurate is too expensive because the channel is too long. So we have a combination of it being too rarefied and too high aspect ratio. So the degree of rarefaction is expressed by the Knudsen number. So we've got a high Knudsen number, but we've also got a high channel aspect ratio. So that combination makes it problematic from a modelling viewpoint. So to tackle that, we've developed a multiscale method, which is a variant of the heterogeneous multiscale method, which we've called the internal flow multiscale method. And I'm only going to be able to give you a very broad overview of the basic concepts here. So for particular details, I refer you to these JCP papers that we've published over the last couple of years on this. So very broadly, what we do is we take a high aspect ratio, long channel flow like one depicted here, and we represent that by a series of very short molecular or particle solvers. So we reconstruct the macro field from information from these otherwise independent micro solvers. So the way that saves time, computational time and computational effort, is because we don't have molecules throughout the length of this long channel. We just have them in these thin strips, these planes. So the important thing to do is to make those individual microsolvers aware that they are part of a macroscopic flow field. And the way we do that is by varying an effective body force applied to each of the microsolvers to emulate temperature gradients and pressure gradients. And we choose those body forces in order to satisfy mass continuity. And that is the basics of the method. Okay, so I now just want to convince you that it works. So this is an example of force-driven argon gas flow in a three-dimensional converging diverging channel geometry. And the IMM, the internal multiscale method, represents that using a series of 9 microsolvers. So those white planes there are two-dimensional microsolvers. They're actually LV-DSMC simulations. An LV-DSMC is a low variance stochastic approach to solving the Boltzmann equation, and actually the code we used here has been obtained from Nicholas Hadjiconstantino's group, and you can get it from his website. Okay, so we're going to compare results from the internal multiscale method with a full three-dimensional DSMC calculation, which is of course much more expensive. So on the bottom left hand plot, I'm going to show the Knudsen number, the degree of gas rarefaction, as we go through the channel. The x-axis is non-dimensional distance through the channel, and you can see there's a significant variation in the Knudsen number as we go through, and that makes it quite a non-trivial calculation. So not only does the density in the Knudsen number vary, but also the cross-sectional aspect ratio changes as you go through the geometry. So now in the bottom right hand corner, I'm going to plot the full three-dimensional calculation and our IMM approach. And what you can see is the dashed line, which is the full three-dimensional calculation, is pretty much exactly the same as the solid line, which is the IMM. So it works, and it's very accurate. Of course, the purpose of doing this is to save computational time. And so looking at what the two simulations cost, the 3D DSMC took 50 hours on 64 cores, whereas the IMM took 5 hours on only 9 cores. So in terms of core hours, the IMM is almost 2 orders of magnitude more efficient or cheaper than the full three-dimensional DSMC. So it works, and it saves a lot of computational effort. So applying this to the Knudsen pump is sort of reasonably straightforward. The capillary that connects the low and the high temperature gas reservoir can be decomposed into these slices, these 2D microsolvers, which are LV-DSMC again. And macroscopically, we essentially solve a mass conservation and an equation of state. But that's not quite it in terms of modelling. There is another challenge, a significant one, and that's relating to time. The mean molecular collision period here in this problem is about 100 nanoseconds, whereas the macro scale transient that we're trying to capture is of the order of 100 seconds. So that's 9 orders of magnitude difference. And if it's not obvious, but that's quite a significant problem in terms of time stepping, because our macro scale model would like to be able to make very large time steps so it can resolve that macro scale transient, but our micro model, the time step is dictated by the requirements of the LVDSMC, which is much shorter, so 9 orders of magnitude smaller. So conventionally what you would do is you would make the macro time step as small as the micro model requires and couple them at every time step, but that is extremely expensive. So what we do, and I refer you to these 2 papers at the bottom here for more details, but we actually allow the macro model and the micro model to advance at different time steps, but we couple them as if they are the same time step. So what we're performing here is an asynchronous coupling, and that's accurate when you have a very scale separated system, which we have here. So we actually get away with having a 360 microsecond macro time step and a 8 nanosecond micro time step for the LV DSMC. Okay, so now we're at a position where we can actually compare these multi-scale methods with the experiment. And so I haven't used any fitting parameters here at all for the multi-scale method. This is purely values obtained from the experiments, and I refer you to the reference on the bottom here. And I'm going to just plot over the top of the experimental data the IMM result. And you can see that's a really very close agreement with the experiment, so that's very sort of encouraging. So we can now make an estimate on how much that has saved us in terms of computational effort by doing this multi-scaling. And there's been a twofold saving. One, because of the IMM, which has allowed us approximately 300 times fewer particles than if we tried to solve the entire length of that channel. And the other contribution is the asynchronous coupling, which has allowed us to use almost 40,000 times fewer time steps. So in combination, that means this IMM is about 10 million times faster than a full particle simulation would have been for the same case. So given that the IMM here took about 4 hours on 9 cores, on the same hardware, a full particle simulation of the entire channel would have taken in excess of 5 millennia. So it's really worth doing this multi-scaling. Okay, so that brings me to the end of the presentation, and I hope the results have demonstrated that there is a potential here with these multi-scale methods in predicting high aspect ratio and micro channel flows.